There's another thing we need to talk about with regard to potential energy before we go too much further. Here is Black Mountain, and I'll label it so you know that it is actually Black Mountain, because I do agree it doesn't look much like Black Mountain. And what sits on top of Black Mountain? Well, Black Mountain Tower, or Telstra Tower, sits on top of Black Mountain. And what sits on top of Black Mountain Tower? Well, there's a bird. That is actually a bird, just in case you were wondering. Now, the observation deck of Black Mountain Tower, or Telstra Tower, is 32 metres above the ground level of the top of the mountain. So there we go, there's our 32 metres. Now the bird's quite a bit higher, and I'm not saying this diagram is to scale, but the bird is about 195 metres above the ground level. That's how tall the tower is above the top of the mountain itself. So I'm going to ask you to calculate what is the gravitational potential energy of the bird. And I'm just going to change that. I'm going to say, what is the gravitational potential energy of the bird relative to the ground level? Well, that's a really easy problem to solve if you know the mass of the bird, which we'll say is 1 kilogram. Acceleration due to gravity is 9.8 meters per second squared, and the height of the bird is 195 meters. And of course, gravitational potential energy is just given by mgh, and if you substitute in all those numbers there, you get something like 1911 joules. Well, now I'm going to ask the same question again. I'm going to ask, what is the gravitational potential energy of the bird? But in some ways, I'm not going to ask the same question. I'm going to ask, what is the gravitational potential energy of the bird relative to the observation deck? So again, this is a quite straightforward calculation. We have the mass of the bird, which is the same, the gravitational acceleration, which is the same, and the height, which this time is not 195, but it's the distance between the bird and the observation deck. So it's 195 minus 32, which is 163 meters. And if we substitute that into our gravitational potential energy equation there, we get 1597 joules. So here's the puzzle. It's the same bird, it's staying in the same place, yet we've calculated two different gravitational potential energies for it. So how can one bird sitting in that one position have two different potential energies? Well, the answer to this is maybe obvious, or it may be a little bit subtle, is that potential energy is always calculated relative to some set 0 point. In the first question, the 0 point was set at the ground level, so at the top of the mountain there. But in the second question, the 0 point was set arbitrarily at the position of the observation deck. But it could have been set anywhere. It's completely arbitrary. We choose it for convenience often, and it gets us to the second point, that it's sometimes more appropriate to refer to a change in potential energy. It's actually changes in potential energy that we're often dealing with when we're analysing physical situations. And of course, the change in potential energy is the mass, which we're assuming remains the same, the acceleration due to gravity, which is the same in this small space, and then it's the change in height between a starting point and an ending point, which is important. And I'm just going to add another note in here that the change in the potential energy for that bird to fall from, or fly from the top of the tower to the ground is the same no matter what the 0 point is chosen for potential energy. So you could actually try this out. You could calculate what the change in potential energy is for the bird going from the top of the tower to the ground level with using the observation deck as your 0 point or the ground level as your 0 point. Now, in more advanced physics, and when we talk about fields, so in this situation, we're assuming that the gravitational field is the same everywhere on Earth. But as we go further away from Earth, that field will lessen in value, so it will get less strong as you move further away. And often, for convenience, we define an infinite distance to have a potential energy of 0, and that actually makes our calculations and our analysis much easier to do. We won't use that definition in this unit. You'll come across it again in Year 12. For now, it's enough for you to just realise that potential energy, the amount of potential energy does depend on where you define your 0 point to be.